3, we're now moving into neural integration. So we looked at neurophysiology. We saw, what do we mean by that neurophysiology? We looked at the physiology of the nervous system. So we looked at how action potentials are conducted and propagated along neurons, and now we're going to look at neural integration. So basically, once we get to that axon and we're moving this action potential from a presynaptic neuron to something, whether it's a muscle or another neuron or a gland, we just want to see what's happening. So the first thing that we want to do is define a synapse. So we've talked about synapses a decent bit before. But a synapse for us is going to be the site of transmission of a neural impulse, or we can say an action potential, from the axon of a presynaptic neuron. So the synapse is that space, right? The synapse is this, the synapse is this whole area. The synaptic cleft is that space. So when there's a synaptic cleft, there has to be something before that cleft and after that cleft. So when it's a neuron before that cleft, or before that synapse, then we say the axon of a pre-synaptic neuron. So a synapse is this transmission of a neural impulse from a presynaptic neuron to one of the following. So that nervous impulse can then go to another neuron, and we'd call that, after the synapse, that'd be a post-synaptic neuron. It could be a muscle. So we've seen both neuromuscular junctions and diffuse junctions. And then, or a gland. So what's the synapse? If we're looking at skeletal muscle, so this is my motor end plate, here's my somatic motor neuron. If I was looking at all this thing, I would say I could call this my neuromuscular junction, but I could also call this a synapse. So this is a synapse, and then whenever I look at my diffuse junction, so my smooth muscle, and then I have these varicosity swellings like this. So this is a diffuse junction. This is also a synapse. So a synapse is the site between a presynaptic neuron and one of the following, either another neuron, so presynaptic neuron with another neuron, presynaptic neuron with a muscle, presynaptic neuron. I'm not going to draw a gland. Okay. So this space, so this is a synapse. The synapse is this whole thing. This space in between it is called the cleft. So things have to diffuse across this synaptic cleft. Okay. So we want to differentiate chemical and electrical synapses. So we've seen chemical synapses before. A chemical synapse uses this presynaptic neuron. This presynaptic neuron is going to have synaptic vesicles containing these chemicals called neurotransmitter. And on our postsynaptic neuron, we're just going to do a neuron for now instead of muscle or gland. So here's our postsynaptic neuron, my cell body. My neurotransmitter is going to diffuse across, and it's going to bind to a receptor on that postsynaptic neuron. So depending on what this neurotransmitter is and what this receptor is, this might open up sodium channels for depolarization, might open up chloride channels for hyperpolarization, so we'll see. As you can see with our chemical synapse, we don't have a direct connection, right? Because we have this space called a cleft. That says direct. I need no direct. No direct connection. And that's because there's this cleft in between. And it's using neurotransmitters. And this is not 100% efficient. And we'll see why in a little bit. So, okay, chemical synapse, presynaptic neuron with some sort of, whether this is a neuron or a muscle or a gland. This is our chemical synapse. The other one that we have are electrical synapses. So instead of having a cleft, we have a presynaptic neuron and a postsynaptic neuron, and they are connected, and we've seen these before. Their integral proteins are fused together. So instead of solid integral proteins, these are hollow integral proteins with channels. So this channel is called a connexon. So what kind of junction is this? This is called a gap or a communicating junction. Just want to give you some time to practice that. And you knew it was a gap or communicating junction because it had this connexon. The other thing you might have been thinking, fused integral proteins, you might have been thinking tight junction, but tight junctions are solid. These gap junctions have this hollow core to let things move from point A to point B. All right, so if I draw my chemical synapse really quickly just for some comparison, I know I have this space called a synapse, and I have to have diffusion of neurotransmitter. So I get sodium moving in, right? Sodium's moving in during this action potential along my axon. It moves in, gets to the end of my neuron, causes this extracellular calcium to come in and bind a synaptotagmin, releases these neurotransmitters, and then this neurotransmitter can come here and it will bind to a receptor, and it may or may not cause an action potential depending on what neurotransmitter and receptor it is, how much is released, all that sort of stuff. So that was our chemical synapse. In contrast with our electrical synapse, we don't have a space. So somehow we need to get the message of action potential from point A to point B. Instead of diffusing neurotransmitters across a cleft, we have these gap junctions which just allow our sodium ions, because remember, we have an action potential over here. Action potential just means a positive 30 millivoltage between the inside and the outside, which just means that there's a bunch of sodium inside. So if I already have sodium inside my cell and I want another action potential, because let's look at this chemical really quick. Chemical had an action potential, movement of sodium in, diffusion of neurotransmission or neurotransmitter. If I get another action potential, I get more sodium moving in. So all I'm doing from point A to point B is getting more sodium in the cell. So for my electrical synapse, let's do that same thing. I have this connexon, this gap junction that my sodium ions can just flow through from point A to point B. Now that I have sodium diffusing into point B, the second neuron, since sodium accumulates in here, I get a change in membrane potential. So as sodium accumulates, this goes from negative 70 to positive 30, and then this will be an action potential that will get propagated down this neuron. So these are not very common. They're common in embryos, and then they're common in adults where we want things to function simultaneously, so the brain. So let's think of this. Let's say that your tribe is getting attacked 10,000 years ago by another tribe. Excuse me. And your spouse, hold on, I need a cough, I'm going to pause this. And your spouse wakes you up. When you wake up, you don't want your brain, you see this woman who's very frantic. You don't want the brain you don't want the part of the brain that recognizes noises to be able to hear her screaming, "Run, there's bad people." You don't want the part of your brain that recognizes facial expressions to then say, "Oh, her facial expression looks scared," and then you don't want your sound receptors to go off. So what we're saying here with these electrical synapses, everything fires off at once. So when she wakes you up, when your brain wakes up, everything turns on at once. The part that recognizes sound turns on the same part that lets you recognize facial expressions, which allows the same time your brain is firing up to be able to run. So electrical synapses allow synchronistic conduction. So synchrony, you've heard of synchronized swimming. This is synchronistic conduction. All right. Sweet. So those are electrical and chemical synapses. No neurotransmitters for this electrical synapse. We do have a direct connection. We don't have synaptic vesicles, right? We have these common in embryos, not a lot in adults except for this. Well, the brain is the one that we're going to talk about. Okay, so we looked at these chemical synapses and electrical synapses. So let's do synaptic conduction up here in this chemical synapse. I just want to give you some words to be able to associate with it.